Next, I want to take this idea of PCA and develop it in two directions. The first direction is called using something called probabilistic PCA. So as the name implies, this is where we take PCA and we build it into a, we view it as a probability model and learn the parameters using a probabilistic representation. So in that sense, I want to recall what we discussed previously, the connection between principal component analysis and the singular value decomposition. So we've already discussed how a data matrix X automatically has a singular value decomposition. So we can write any matrix X as a product of a matrix U, S, and V transpose, where U transpose U is the identity matrix and V transpose V is the identity matrix. So here I'm assuming X has more columns than rows. If it had more rows than columns, then some of these transposes would be switched. Also, the matrix X, S, is a diagonal matrix, so all the values in it are 0 except for along the diagonal, and all the values in S are non-negative along the diagonal. And so therefore, this matrix that we get, X times X transpose, which is what we want to learn the eigendecomposition of, is equal to U S squared U transpose. And similarly, we have this product, X transpose U is equal to U S squared. And so remember the representation from a previous slide where we had lambda here and Q on both sides. Here now we have those eigenvectors along the columns of U, and we have the lambdas along the diagonal elements of S squared. So U is the matrix of eigenvectors, S squared is the diagonal matrix of the eigenvalues for our eigendecomposition of this matrix. So now we want to think of a modeling approach to PCA. What we're going to discuss next is a model that uses the EM algorithm. So we have to define a generative process and then do EM to learn it, a point estimate of it. And what this model is going to be able to do that the original PCA couldn't is handle some additional issues that might arise. For example, we might want to handle missing data. PCA can't handle that issue as easily, directly. This can handle missing data fairly straightforwardly. It will also allow us to do additional things like learn model parameters such as noise. We can build it into a framework that's part of a more complex model, and also learn uncertainties about certain parameters. So there are some reasons why we might want to choose a probabilistic model. There are also many reasons why we wouldn't. So this is just a different technique that we're going to discuss. So really, the idea of using probabilistic PCA can also be viewed as doing probabilistic SVD because of the connection. So remember, we have that X is equal to U times S times V transpose if we want to write it as an SVD, and that we can then get U and S and say that those are the eigenvectors and eigenvalues. So we can directly learn this sort of a factorization without having to take the product of X with itself. And so now that's what we're going to do. We're going to say that X is approximately equal to W times Z, where W is a D by K matrix. So D is the dimensionality of the data, K is the number of eigenvalues and eigenvectors that we want to learn. But in this setting, we can call W something else. We'll call it a factor loadings matrix or a dictionary, so it has many different names, depending on the problem that it's being applied to. However, we're also going to relax the constraint that W has to be orthonormal. So that's a crucial difference between probabilistic PCA and regular PCA. The columns don't have to have unit length, and they don't have to be orthogonal to each other. So that's a significant relaxation we're going to make. And also, the matrix Z now is going to have vectors in it, Zi along the ith column of Z, where each one now is in Rk. And we're now going to think of Zi as being the low-dimensional representation of the corresponding value xi in X. So if the ith column of X corresponds to the ith data point, the ith column of Z corresponds also to the ith data point, except projected into a lower k-dimensional space. Okay, so now we have to define the generative process, and this is the process for probabilistic PCA. We assume that the ith data point xi is a multivariate Gaussian with mean equal to the matrix W, which is d by k, times the vector zi, which is a k-dimensional vector, plus some noise. And then the the vector zi now is also a random variable from a Gaussian with zero mean and identity covariance matrix. So this is the generative process for each data point. And now in this case, we don't know W, and we also don't know any of these vectors Z. So now we want to learn both of these things. And the way that we're going to do this is through maximum likelihood. So our goal is to find the maximum likelihood solution of the matrix W under the marginal distribution. So our goal is to integrate out all of the z's, the impact of z. We want to integrate it out of the model and then do a point estimate that maximizes the marginal likelihood with respect to the matrix W. So in notation, what we're saying is that the maximum likelihood value for the matrix W is equal to the maximum of the log of the joint likelihood of all the data given W, where z is integrated out. And now because we're going to make an independence assumption among our data, this likelihood is a product of the likelihoods of each observation. And so that turns into the argmax over W of the sum over each data point of the log of the likelihood of each individual data point given W. However, if we actually calculated this marginal distribution, we would find that the likelihood of xi given W is equal to a multivariate Gaussian with mean 0, because zi has a 0 mean, and covariance equal to sigma squared I times W transpose. So this is the covariance matrix of xi, this diagonal matrix plus W transpose. And now if we actually looked at what this density looked like, and then we take the log of it, we'll find that we can't solve it with respect to W analytically. So take the log of this thing, take the derivative of it with respect to W, the matrix W, and you quickly find that we're in a bind. We can't do this and solve for W analytically. And so what we're going to do is reintroduce these vectors Z as the missing part of our model, and then do EM on that. So this is another example of an EM algorithm of where EM is useful. So to do this, again, we have to set up the EM equality. We have the marginal likelihood here, and so I'm writing the marginal likelihood we want to maximize over W as an integral over Z. So Z is actually integrated out here, but I want to show explicitly that it's being integrated out. This marginal likelihood, which is hard to optimize over W, is equivalently represented by this sum of these two terms. So this left-hand side is equal to the right-hand side, where now I have introduced a Q distribution on each of these vectors Zi, and I have, notice here, the joint likelihood of Xi and Zi together. So this is what we've been calling L. And in the second line, I add to it the Kolbeck-Leibler divergence of the Q distribution on Zi and the conditional posterior distribution of Zi given the data point Xi and given the matrix W. So these are the Kolbeck-Leibler divergences. So the sum of these two things is equal to this left-hand side. Now if we want to use the right-hand side to do EM in order to maximize the left-hand side over W, remember we have to do two steps. First, we have to make this Kolbeck-Leibler divergence equal to 0. And that's the E step. And so we set, in order to do that, we know the only way that this could equal 0 is by setting Q to equal this distribution here. So we have to match these two distributions. So in a particular iteration, we have a particular value for W. We set Q to be equal to this conditional posterior distribution. And we hope that we can calculate this. Unfortunately, we can in this case. That's going to set all of these KL divergences to 0. And then we calculate this expectation, this integral, using that update for the Q distribution. So we calculate out. That's the E step. Then the M step is to maximize L, to maximize this term over the matrix W. So that's the M step. And so again, if we want any hope for EM to help us with this problem, we have to know that we can solve this conditional posterior enclosed form. And we also have to hope that the maximization of this term over W is easy, because remember, maximizing this thing over W is hard. If this thing is also hard, then we're still in trouble. So we hope that we can do this in closed form. Unfortunately, we can. And the result is this algorithm. So I'm not going to derive everything from scratch. I'm just going to present the algorithm for doing EM for probabilistic PCA. So we're given data x1 through xn, where each data point is in Rd, where D is a high-dimensional space. And we're going to model each of these data points as being a multivariate Gaussian with mean equal to the matrix W times Zi and times sigma squared I. And each of these vectors Zi, which is a k-dimensional vector, is standard Gaussian. So W is D by K, and Z is a k-dimensional Gaussian. What we're going to output is a point estimate of W that maximizes the marginal likelihood, and also a conditional posterior distribution of each Zi, which gives us our posterior belief about what the low dimensional embedding should be. So we don't just get a low dimensional embedding for each point xi in the Q of Zi, we also get some distribution on that embedding. So the E step, we have to set Q of Zi to be equal to its conditional posterior distribution. This is a straightforward calculation. We can show it's a multivariate Gaussian with mean mu I and covariance sigma I, where sigma I is equal to the identity plus W transpose W divided by the noise parameter inverse. So every single Zi has exactly the same covariance in the conditional posterior. And then the mean of the conditional posterior is equal to the covariance times W transpose X sigma divided by sigma squared. So we calculate this using the most recent value for W in both of these equations. And so because Xi appears here, the mean is what's different for each data point. The uncertainty is the same. And then we calculate L, and I'm not showing that calculation here. Then the M step it involves taking the derivative of the objective L with respect to the matrix W and solving. And in that case, we can do that as well in closed form, and we get this update. So we update W after updating each of these Q of Z's. We update the matrix W by taking Xi times the mean mu I transpose. So this is the conditional posterior distribution of Z, the mean of it, transpose. So this outer product is a matrix that's D by K. And then we sum it over every single data point. So this is a D by K matrix. And we multiply it by the inverse of this matrix, which is the noise variance, sigma squared I, plus the sum over each data point of this term, which is the outer product of the posterior mean of the embedding Zi, which is K by K, plus the posterior covariance, sigma I. So this is a K by K matrix. We sum it over every data point and invert it, and the result is still D by K. And so that's our update for W. And then because W has changed, we update each of these Q distributions, and we iterate back and forth until the improvement of this marginal likelihood is small. So even though we couldn't take the derivative of this with respect to the matrix W and optimize it, we can still evaluate it at each value of W. So we still can use this equation where we take the log of it over each of these xi's here to evaluate at each point W to get the log marginal likelihood. And then we terminate when the improvement is small. The relative improvement stops increasing quickly. So now let's look at an example of this applied to an image processing problem of denoising an image. So here we have a very noisy image. I'm not sure how noisy it would show up for you, but it's a noisy image. And how we're going to denoise this image is by extracting 8 by 8 patches, where 8 by 8 is arbitrary. It could be more, it could be bigger, it could be smaller, but we'll say 8 by 8. We then vectorize that into a 64-dimensional vector. So for this 8 by 8 patch, we extract it, we vectorize it to be 64 dimensions, and put that along a column of a matrix. And we do that for every patch. So we get many patches, and that constitutes this matrix X, which is 64 by, for this image, if there are this many pixels. So roughly this many pixels. So there's about 250,000 of these columns in the data matrix. Then for each, then what we do is we factorize using probabilistic PCA to approximate xi as the product of W with the conditional posterior mean mu I. So we're saying that this x is approximately equal to W times Z. Remember, we don't learn Z, we learn a conditional posterior of it. And so when we learn this model, we learn the conditional posteriors, we learn a point estimate at W, we then replace Z, each column of Z, with the posterior mean mu, and then we approximate xi, which is the ith column of this matrix, as W times mu I. So we take this matrix and we approximate it with this matrix, where now we have W mu, and then we take the ith column here and put it back into the image. So we take out the noisy patches, we replace it with the denoised patches, and then we reconstruct the image. And so where's all the noise gone? It's gone in the noise term of the generative model. So the original model has this as our expression of the point xi. We're assuming this is a denoised mean, and then here is where all the noise is contained. And so when we reconstruct the image and see what it looks like, we get this. So this is where we take the noisy patches, we replace them with the denoised patches, and we get a denoised image on the right. Here's another example using missing data. It's a very extreme example. So here's a 480 by 320 by 3 image. So the third dimension is because it's a color image, so RGB. 80% of those values are thrown away completely at random. And then we've extracted an 8 by 8 by 3 cube from many of those from this image. And then we filled in the missing data using EM. After filling in the missing data, we construct the image, and we get this. And you can compare it with the original image without the missing data, and it's very close. So we learn all the missing pixels in here, we fill them in using EM, and we get this. So it's an extreme example, but also a clear example of how actually we have plenty of information in this missing image in order to get a very good sense of what the true image looks like.